Today, we're going to dive into a pretty wild idea, a paradox that's at the heart of the modern world. To make things stronger, safer, and more reliable, we have to break them first. We're going to explore the science of destroying stuff on purpose, all to figure out the secrets that keep our world from falling apart. I mean, really, think about it for a second. Why is the chair you're sitting in holding you up? How does a massive bridge just hang there? Why hasn't your coffee mug just shattered in your hand? Well, it's not luck and it's not magic. It's data. Cold, hard data that we get from pushing materials to their absolute catastrophic breaking point. You know, when it comes to checking if a material is up to snuff, engineers have two main playbooks. There's non-destructive testing. Think of it like a doctor giving you an X-ray, looking for problems without causing any harm. But today, we're talking about its much more dramatic cousin, destructive testing, where the whole entire point is to make it fail. So, let's start with the most basic, most fundamental test of all, the tensile test. You can honestly just picture it as a super scientific, high-stakes game of tug-of-war with a piece of metal. The question is simple. Just how hard can we pull on this thing before it snaps in two?
The process itself is, well, it's brutally simple. You take a standard piece of the material, which is usually shaped kind of like a dog bone, and you clamp it into this powerful machine. Then the machine just starts pulling, slowly, steadily, with more and more force until... snap. It breaks. And every single moment of that process, right up to the final failure, is measured and recorded, telling us everything we need to know.
So what's the first secret we learn? It's called yield strength. And this, right here, is the point of no return. Think about a rubber band. You stretch it and it snaps right back, right? That's called elastic deformation. But if you pull it too far, it gets all stretched out and won't go back. That exact moment it crosses over, that's the yield strength. It's now permanently changed.
But even after it starts to permanently deform, the material keeps fighting. The absolute maximum stress it can possibly handle before it starts to crack and fail, that's its ultimate tensile strength, or UTS for short. For any engineer designing, well, literally anything that needs to be strong, this number is the holy grail. It's the material's peak performance.
Okay, but pure strength isn't the whole story. Not by a long shot. There's another key property called ductility. This is all about how much a material can stretch and change shape before it actually breaks. So something brittle like a ceramic plate has almost no ductility. It just shatters. But a ductile material like copper can be stretched into a super thin wire. It's a measure of how much give it has.
So pulling something apart slowly gives us a ton of information. But what happens when something gets hit with a sudden, violent impact? You know, like in a car crash or if you drop a heavy tool. To figure that out, we need a totally different kind of test.
And for that, we have the Sharpie V-notch test. Now, it sounds fancy, but it's actually beautiful in its simplicity. You take a little bar of your material, cut a tiny V-shaped notch in it, and then you slam it with a giant, swinging pendulum hammer. The test measures how much energy that little bar absorbed when it broke.
And this brings us to a really, really important distinction. The Sharpie test isn't really measuring strength, not like the tensile test was. It's measuring something different, something just as crucial. It's measuring toughness.
And that's the perfect way to think about it. Toughness is a material's ability to take a punch. A dinner plate is actually pretty strong if you just press on it, but it has zero toughness. Drop it, and it shatters into a million pieces. It absorbs almost no energy. But a car bumper? It's designed for toughness. It's meant to crumple and deform, absorbing the energy of an impact to keep you safe. The Sharpie test tells us if a material behaves like a bumper or a dinner plate.
All right, so we've pulled materials apart and we've smashed them with a pendulum. What's next? Well, how do we figure out how well a material resists surface damage? You know, like preventing a scratch on your phone screen or a dent in your car. That's where hardness testing comes into play.
The core idea behind all hardness tests is pretty much the same. You take a really hard object, called an indenter, and you press it into the surface of your material with a specific amount of force. Then you measure the size of the dent it leaves. The tools just change for the job. The Brinell test uses a small steel ball, great for softer metals. For super hard stuff like coatings, you need the Vickers test, which uses a tiny diamond pyramid. And the Rockwell test is super popular in factories because it's really fast. It just measures the depth of the indent directly.
But you know, things don't always fail because of one big dramatic event. Sometimes it's a slow burn. It's death by 1,000 cuts from repeated stress or a corrosive environment or just constant friction. So how in the world do you test for that?
For repeated stress, we turn to fatigue testing.
You've done this yourself. Ever been a paperclip back and forth? It's fine the first time, it's fine the 10th time, but eventually it just gets tired and snaps. That's metal fatigue. The Wohler test is just a very precise, scientific version of that, applying cycles of push and pull over and over and over until the sample finally gives up.
Next up, we have to fight the environment itself. Corrosion testing is all about predicting how a material is going to hold up against things like rust and other chemical attacks. It's about fast-forwarding time to see how it'll react to salt water, or acid rain, or just plain old humid air.
And scientists have some pretty gnarly ways to speed up this process. The salt spray test, for example, is just brutal. It puts materials in a hot, salty fog for hundreds of hours to see how the coatings hold up. An immersion test is exactly what it sounds like. They just dunk it in some nasty solution. It's all about simulating decades of wear and tear in just a few days or weeks.
And finally, there's good old-fashioned wear and tear from friction. For that, you've got the Tabor test. Basically, you take a sample of your material, spin it like a record, and lower 2 abrasive grinding wheels onto it. It's designed to see how quickly a surface gets worn away, which is absolutely critical for testing things like paints, coatings, and even the laminate on your floor.
Okay, so we have stretched things, we've smashed them, we've dented them, we've exhausted them, corroded them, and ground them down. It sounds like a whole lot of senseless destruction, right? But out of all that chaos, all that breaking, we actually get the blueprint for building a safer world.
And really, this is the whole point of everything we've talked about. By knowing exactly how and when a material will fail under pressure in a lab, engineers can do their real magic. They can take those limits and then design everything, from an airplane wing to a skyscraper, to operate safely far, far below those limits. It's called a factor of safety, and it's why our world is as reliable as it is.
So the next time you get in an elevator, or walk across a bridge, or even just sit in your chair, remember this: you can trust it, because somewhere, in a laboratory, a version of it was pushed to its absolute limit and utterly destroyed. It was designed to fail, so that out here, in the real world, it never, ever will. What are you going to look at a little differently now?